Hello everybody. The title of my talk is Group of Automorphisms of Infinite Dimensional Hyperbolic Space. This is a joint work with Mukund Madhav Mishra and Krishnendu Gangopadhyay. We begin with the notion of a hyperbolic plane. A hyperbolic plane is a subset of C or R2 equipped with a metric which satisfies the first four axioms of Euclid along with the modified fifth postulate which says that in a plane given a point and a straight line not passing through the point, then there exist more than one straight lines which pass through that point and are parallel to the given straight line. Some classical examples of a hyperbolic plane are the Poincare disk model, which is the open unit disk in the complex plane equipped with the Poincare metric, and the upper half plane model, which is the upper half plane in R2. Once we have a system which is different from the Euclidean one, then naturally we would like to develop the geometry on it. One indispensable tool to study hyperbolic geometry is studying its isometries. Here, we will be discussing the isometries of the upper half plane model, and in specific, we will be interested in discussing the holomorphic isometries. So H denotes the upper half plane model, and we consider the collection of holomorphic isometries which are bijective, so we call them holomorphic automorphisms. This collection forms a group, we call it AutH. Its general elements are fractional linear transformations having real coefficients satisfying AD minus BC equals to 1, and hence can be identified with the group SL2R. Since we want to study this group AutH, in order to do this effectively, we will be studying the conjugacy classification within this group. And why studying conjugacy classification helps in more efficient study of the group. For that, we need some machinery, namely the fixed point classification, which classifies the element of the group on the basis of fixed points. It says that a holomorphic isometry in H satisfies exactly one of these three conditions. Either it has a fixed point inside H, in that case it is called elliptic, or it does not have any fixed point inside H and has exactly two fixed points on the boundary, which is the extended real line. In that case, it is called hyperbolic. Or if it does not have any fixed point inside H and has a unit fixed point on the boundary, in that case, it is called parabolic. Now, conjugacy just moves fixed points. So it is easy to see that all elliptic isometries are conjugate to elliptic isometries, and all the conjugates of hyperbolic isometries would be hyperbolic isometries, and all the conjugates of parabolic isometries would be parabolic isometries. So if we have some nice representations of these elliptic, hyperbolic, and parabolic isometries each via conjugacy, so it helps us in more organized study of the group. And it turns out that an elliptic isometry is conjugate to rotation, hyperbolic isometry is conjugate to dilation by a positive real number, and parabolic isometry is conjugate to translation by 1. One may refer to this book by Anderson to study hyperbolic geometry of the plane. Now, once we have the theory developed for the plane, over the years, mathematicians have successfully developed the analogous theory for higher dimensional spaces and have extensively studied it. Some of the references where the studies have been made on the conjugacy classes in the group of holomorphic automorphisms of the higher dimensional hyperbolic spaces are Chen Greenberg, Gangopadhyay Kulkarni, and John R. Parker. Next, we try to extend the theory discussed so far to infinite dimensional setup. So we begin with the notion of a hyperbolic space in infinite dimensions. Let H be a complex Hilbert space. This hyperbolic space is a generalization of the Poincare disk model. So H is a complex Hilbert space and B is the open unit ball in H equipped with the Carathéodory metric. Carathéodory metric can be seen as a generalization of Poincare metric as both coincides on the open unit ball in the complex plane. So this B serves as the hyperbolic space in infinite dimension. Now we talk about the group of holomorphic automorphisms. So AutB denotes the group of biholomorphic maps of B whose general element is a composition of a unitary operator U and another biholomorphic map fx0 for some x0 coming from the open unit ball. And fx0 is given via this expression, which is a composition of a linear operator tx0 and this inside expression. And tx0 is given by this. Now, once we have this general form, we can have the formula for computing Carat-Theory metric in terms of the Poincare metric as follows. For any 2 points x and y coming from the open unit ball, their Carat-Theory distance can be given as the Poincare distance from origin to the point norm of fyx. Since we want to study the group AutB, we will be identifying it with something we are more comfortable with, that is the linear mappings. For that, we begin with the Hermitian form on H direction C, which is an infinite dimensional analog of a Hermitian form on Cn+1 having signature n,1. And this group G of all bijective linear operators on H direction C, which are isometries for this Hermitian form. And this G is an extension of the classical group UN,1. Now, a general element of G is a linear operator on H direction C, hence looks like a 2 cross 2 matrix whose entries are compatible via these relations. Next, we see the identification between this linear group G and the AutB. For every element T in G, the corresponding element in AutB is given via this fractional linear transformation such that the map is an onto homomorphism. Hence, if we quotient out this G by its kernel, which is the center and is the collection of all unit constant multiples of identity, so this quotient map can be identified with AutB. Now, one may refer to this book by Franzini and Vicentini for the framework just discussed for infinite dimensional setting. Also, the way we discussed the fixed point classification in the classical case, exactly here, the same fixed point classification holds, and the result is due to Hayden and Suffrage. Next, we discuss the simplified form of elements of G, which looks like this, where xi is a vector in H, capital U is a unitary operator on H, small a is a positive real number bigger than equals to 1 given as this, and capital A is a positive linear operator on H which decomposes it orthogonally into xi such that on the per part A coincides with identity and capital A of xi is equal to small a of xi. Moving towards the conjugacy classification, let us identify the normal isometries in G. A bounded linear operator on a Hilbert space H is called normal if it commutes with its Hilbert adjoint T star. Hilbert adjoint can be seen as an infinite dimensional extension of conjugate transpose of a matrix. We have a unitary element of G is a diagonal operator such that we have the unitary element on each diagonal. And a normal element of G is an operator of this form where U of xi is equal to xi. And this fact makes T decompose H direction C orthogonally into a two-dimensional subspace xi plus C, such that on the per part, the operator coincides with U. This orthogonal decomposition makes the study of spectral properties of a normal operator very handy. And finally, we talk of the conjugacy classification. So we have an elliptic isometry is conjugate to a unitary element. A hyperbolic isometry is conjugate to a non-unitary normal element, and a parabolic isometry having singleton spectrum is conjugate to Screw-Heisenberg translation. Screw-Heisenberg translation can be seen as an extension of upper triangular matrices having singleton spectrum. The study of parabolic isometries we make on Siegel domains, which are counterparts of the upper half plane. These are some selected references: Chen Greenberg, Franzini Vicentini, Gangopadhyay Kulkarni. Thank you for your kind attention.